Good day. So let's have another example for the design and analysis of flexural members for a steel design. So for this example, I compute the design flexural strength that is under LRFD of W21 by 44 with Fy is equal to 50 KSI with an unbraced length of 2.7 meters. Assume C sub B is equal to 1.0. So we have from our previous discussion, from our first example, from the previous video, we are able to check the compactness of W21 by 44, and we are able to prove that its flange is compact and its web is also compact. So therefore, we can still use the section 506.2 of our NSCP 2015. Then from the given, we have this Fy is equal to 50 KSI. We multiply this one by 6.895 megapascals. So let's have the equivalent of F sub y is now equal to, this is 50 times 6.895. And we round this up to the nearest whole number. So let's say 345 megapascals. Then according to this problem, so the unbraced length is equal to 2.7 meters. So our L sub B is now equal to 2.7 meters, or let's say this is 2,700 millimeters. Now we need to check which zone this unbraced length is under. So if we are to proceed from our previous discussion, so let's check if we have, let's have first the value of L sub P. So L sub P is 1.76 of Ry multiplied by the square root of the modulus of elasticity times Fy. So these are the properties of the W21 by 44. So first we need to check what is the value of the L sub P. That is equal to 1.76, the radius of gyration with respect to the y-axis multiplied by the modulus of elasticity of steel divided by the value of Fy. So we are now substituting. We have L sub P is equal to 1.76. Ry for this section is 32 mm. And then multiplied by the square root of modulus of elasticity of steel is 200,000 megapascals. Then our Fy is 345 megapascals. So this is, we have L sub P is now equal to, we have 1.76, Ry is 32 millimeters, then multiplied by the square root of 200,000 megapascals, divided by 345. And that is 1,356.03. So let's say 1,356.03 millimeters. Now, if we are to observe, what is our unbraced length? So unbraced length is greater than the L sub P. This is L sub B is equal to 2,700 millimeters. So which means this is not under zone 1. So since we have the value of L sub B is greater than the value of L sub P. So to determine which zone is either zone 2 or zone 3, we need to determine the value of L sub R using this equation. So maybe just copy this part. So let us assume that it is maybe zone 2 or zone 3. So to decide or to determine which zone, we need to determine the value of L sub R. So L sub R is equivalent to this very long equation. So what are the values needed? We need the value of the R sub Ts. So we have here an equation, R sub Ts squared is equal to ay the square root of the moment of inertia with respect to the y-axis ay the warping torsion, that is the c sub w, divided by the section modulus, okay, with respect to x-axis. And we have those values, except for the value of the c sub w, I think. Yes, we have the value of the c sub w here. It's 567 times 10 raised to 9 millimeters. Okay, so let us compute for the value of the r sub ts squared. Okay, so for the value of the r sub ts squared, okay, this is equal to the square root of the moment of inertia, the square root of the moment of inertia with respect to the y-axis, then the c sub w. Okay, so again, these values are taken from our database for the properties of W21 by 44. Then this is to be divided by the section modulus with respect to the x-axis. We have r sub ts squared is now equal to the square root of, what is our iy? Iy is 8.62. This is times 10 raised to 6. Then we have the value of the c sub w. This is 567 times 10 raised to 9. That is millimeters raised to 6 and millimeters raised to 4. Then square root, that will be millimeters raised to 5. Then divided by s sub x. S sub x is millimeters raised to 3. So that is 1,340 times 10 raised to 3. So we have r sub ts squared is now equal to, this is the square root of 8.62. This is times 10 raised to 6. Then multiplied by our c sub w, 567 times 10 raised to 9. Then to be divided by 1,340 raised to 3. That is 1,649.8344. So 1,649.8344 and so on. Then all you have to do is take the square root of both sides of the equation to determine the value of r sub ts. So all we have to do is square root of this value, and that is 40.62. We have 40.62 millimeters. Since this is the unit of this term is already on millimeters squared. Okay. So that's the value of our r sub ts. So what else? We have the value of j, 320. Okay, the value of c. What about the value of c? This is small c. Okay, if you are to look on our reference from the previous discussion again, so we have j is the torsional constant in millimeters raised to 4. The value of c is 1.0 for doubly symmetric shapes. So that includes our section, the W 21 by 44. Okay, so we have now also the value of c is also equal to 1.0. So what else? So what about the h sub o? So h sub o, by definition again, h sub o, the distance between the flange centroids. So how do we compute for the value of the h sub o? That is the distance between flange centroids. So the centroid of this upper flange, I hope you can see that green dot, or maybe you can use black ink. It says the centroid of the upper flange and the centroid of the lower flange. If we are to measure this distance, that will be our h sub o, or basically that is the total depth of the wide flange or the I section minus the t sub f, that is the thickness of the flange, over 2, since the centroid will be on half of its thickness, 1 on the top flange and 1 on the bottom flange. Or basically, our h sub o is equal to, so 1/2 plus 1/2 is 1. That is the total depth minus the thickness of the flange. That is the equivalent of our h sub o. So let's have the equivalent of our h sub o for this equation is, what is the total depth of W21 by 44? We have that as 526 minus twice of the thickness of the flange, 11.4 millimeters. And this is now equal to sorry, it's not twice. It's simply the depth minus the thickness, right? Yes, the depth minus twice the thickness. So it's not twice. It's simply the depth minus the thickness of the flange. We have 514.6. So this is 514.6 millimeters. So I think all needed values or all needed elements of this equation are now available. So we are now ready to compute for the value of the L sub R. So we are now to compute for the value of LR. Let's have a copy of that equation. So we are now to substitute. So we have the value of LR is equal to, we have 1.95. Our RTS is equal to 40.62. Then to be multiplied by IE is 200,000 megapascals. Then divided by 0.7. Our FY is 345 megapascals. Then the square root of J, what is our what is the value of J? That is 320 times 10 raised to 3. 320 times 10 raised to 3. Then the value of C is simply equal to 1.0. Then divided by our section modulus with respect to the x-axis, S of x is, we have 1,340 times 10 raised to 3. Then the value of h sub o, our h sub o is equal to 514.6. Then this value to be multiplied by the square root the square root of 1 plus the square root of 1 plus 6.76. Then multiplied by 0.7. What is our FY? 345. S sub x is 1,340 times 10 raised to 3. Then again to be multiplied by the value of the h sub o, that is the 514.6. Then divided by modulus of elasticity is 200,000 megapascals. The value of J is 320 times 10 raised to 3. Then the value of C is simply again 1.0. And this value is raised to 2. So let's have the value or the equivalent of L sub R. So let's have first this term. So this is the same as the square root of 1 plus the 6.76. Then multiplied by 0.7 of 345. Then S of x, 1,340 times 10 raised to 3. Then to be multiplied by 514.6. So all values to be divided by 200,000 megapascals. okay, times 320 times 10 raised to 3 times 1. And this value is raised to 2. Okay, then we are 2. Okay. This is now, we have now this value as our answer in our calculator. Then all we have to do is plus 1, then take again the square root. So that is the same as the square root of 1 plus the computed value answer. Then it's 2.779. And we are now ready to multiply it to the to this term or terms. Multiplied by the square root of 320 times 10 raised to 3 times 1. Then divided by 1/3 times 10 raised to 3. Then multiplied by 8 sub o, that's 514.6. Okay. Then we are now to multiply that value to this 1. So that is the answer multiplied by 200,000 divided by 0.7 of 345. And then multiplied by the RTS, multiplied by 40.62, multiplied by 1.95. And we have L sub R is 3,956.39. We have the L sub R is 3,956.39 millimeters. So 3,956.39 mm. And we are now ready to summarize. So which zone is this section? Again, if you are to recall, we have L sub P is equal to 1,356.03 mm. 1,356.03 mm. Our unbraced length, that is the L sub B, is equal to 2,700 millimeters. And our L sub R is equal to 3,956.39 mm. So basically, L sub B is greater than the L sub P, but less than the L sub R. So which means we are under zone number 2. So for the computation of the nominal moment capacity for zone number 2, so we have this equation. M sub n is equal to M sub B minus C sub B multiplied by the quantity M sub B minus M sub B times M sub B minus M sub B minus 0.7 of Fy S sub x multiplied by this quantity L sub B minus L sub P divided by L sub R minus L sub P. And it should be less than the M sub P. So let us compute the equivalent of the M sub P. Our M sub P is equal to, we have Fy multiplied by the section modulus, the plastic section modulus with respect to x-axis. So this is equal to 345 megapascals multiplied by, what is our Z sub x last time? We don't have that value, so we go back to our database. Okay, C sub x is 1,560. Okay, so this is 1,560 times 10 raised to 3. So our value of M sub P is equal to 345 multiplied by 1,560 times 10 raised to 3. And that's equal to 538.2 times 10 raised to 6. So 6 Newton millimeter. If we have that value in Newton mm. So let's have the equivalent of our nominal moment capacity. So using this equation. Okay, so our necessary equation is equal to M sub n equal to C sub B. Multiplied by the quantity M sub P minus M sub P minus 0.7 of Fy S sub x And then the quantity L sub B minus L sub P all over L sub R minus L sub P. But should be less than the value of M sub P. So we have the value of the C sub B for this example is assumed to be 1.0. Okay, so I think we are now ready to substitute. Okay, we have the equivalent of the M sub N is now equal to C sub B is 1.0 multiplied by 500. This is 538.2. This is times 10 raised to 6. Less the quantity. We have 538.2 times 10 raised to 6 minus. Okay, we have 0.7. That is 0.7 of Fy 345 megapascals. A while ago, what is our S sub X? S sub X, what is that value again? 1340 times 10 raised to 3. This is to be multiplied by 1,340 times 10 raised to 3. And then this value is to be multiplied by L sub B. We have 2,700 millimeters minus L sub P. L sub P is 1,356.03. So this is 1,356.03. Then to be divided by L sub R. What is our L sub R? L sub R is 3,956.39. We have 3,956.39 less L sub B. That is 1,356.03. Then this should be less than the value of our M sub P. So we'll be having the value of N sub N so equal to so let's have first this term, the equivalent of this term. That will be 2,700 minus 1,356.03 divided by 3,956.39 less 1,356.03. Then to be multiplied by 538.2 times 10 raised to 6 minus 0.7 of 345. Then S sub X, we have 1,340 times 10 raised to 3. Then we subtract this term from 538.2 times 10 raised to 6 minus the answer. As we have, then we divide this term by 1,000 squared. Since that is already in Newton mm, dividing it by 1,000 squared will give us a value in kilonewton meter. So 427.291 or 0.29. 400, we have 427.29 kilonewton meter. So this will be our nominal moment capacity, and it is less than the value of our M sub P. So if we are computing for the design moment, the design's flexural strength, we have that is the M sub U will be equal to the reduction factor multiplied by M sub N is equal to 0.90 multiplied by 427.29. And this MU is now equal to multiplied by 0.9. We have 384.56. 384.56 kilonewton meter. So this will be the design flexural strength of the W21/44 with an unbraced length of 2.7 meters. And this will be our solution for this example. Just a little correction regarding this or the grouping for my grouping symbol. So we should place a close parenthesis here. Okay. But again, the answer will be 384.56 kilonewton meter. So this will be our solution for this example.